Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. Today in this class, we'll talk about Introduction to Beams. Before we go to Introduction of Beams, we'll talk about elastic stability of columns and overview. We began the course by talking about spring bar model, as you can see from the picture here. And in the deformed or the loaded condition, we can see that there is a small displacement that takes place, a rotation here, theta. The bar is assumed to be infinitely stiff or rigid. The reason that it is stiff or rigid is that you can easily solve the problems using algebraic equations rather than getting clouded with complex mathematics such as partial differential equations or ordinary differential equations. So in the deformed shape, we have a restoring force F and we have a disturbing force P. And using equilibrium, we can find the equation P delta minus Fa dash equal to 0. This is equation 1. Next, using force displacement relation, we have F equal to K delta, equation 2. Then we have the strain displacement relation delta equal to A sin theta, which is equation 3. Solving the three equations, we have P equal to Ka cos theta. Whereas when it comes to Euler column, there are certain assumptions. The one is that the column is perfectly straight, the ends are simply supported, the load is concentric, column buckles or bends in a single plane, which means that it is deformable. This is very much different from the spring bar model. And we have the curvature is approximated to be y double dash, and the material is homogeneous and obeys Hooke's law. So this is the picture of the simply supported column loaded axially. Using this one, we can come up with a free body diagram at the loaded condition. And taking moment about point B, we have m equal to P into y, which is equal to minus Ei into d square y by dx square is equal to Py. Dividing Ei on both sides, we have d square y by dx square plus P by Ei into y is equal to 0. So let's take P by Ei as k square. We have d square y by dx square plus k square y is equal to 0. Now this is first order ordinary differential equation. So d square y by dx square plus k square y equal to 0. Upon solving, we get P critical equal to pi square Ei by L square. The generic equation for Euler critical load is P critical equal to pi square Ei by KL the whole square. This K is the effective length factor which takes into account the various boundary conditions for the column. So the deformed shapes of columns with different boundary conditions can be seen below. The first one is basically for pin-ended conditions where K equal to 1.0. The next one is for fixed boundary conditions where K equal to 0.5. The third one is for pinned and fixed conditions where K equal to 0.7. And then the next one is basically fixed and free condition where K equal to 2.0. So basically this comes under the concept of hidden Euler strut, where the Euler strut is assumed to be hiding in each of these columns. The buckling load between the points of inflection or counterfracture is basically the Euler column that is hiding. So we have the generic equation for Euler critical load, P critical equal to pi square Ei by KL the whole square. These are the four differential equations that we have solved previously in our classes, and we have got the K values as 0.5, 0.7, 1.0 and 2.0. The takeaway here is that the applied load P is concentric compression, as you can see from here, and the column bends or buckles in a single plane. The governing differential equations are a function of only one variable, which is y. Now, how is a column different from a beam? Fundamentally, columns are axially loaded members, whereas beams are transversely loaded members. So let us identify columns and beams based on these statements. Now you look at a structure which is a typical structure frame in a steel building. You might assume that the ones that are vertical in nature, the members that are columns, and the ones that are actually horizontal are basically beams. However, the columns and beams are not defined based on their direction or the verticality or whether they are flat. It depends upon the application of the load. So in practice, columns are predominantly axially loaded members. Beams are predominantly transversely loaded members. Mathematically, when P is very much greater than M, it behaves like a column. When P is very much less than M, it behaves like a beam. And when P is more or less equal to M, it behaves more like a beam column. So in the previous classes, we have studied columns. So let us understand the behavior of beams in this course. So let us consider a simply supported beam subjected to equal end moments, as you can see in the picture here. you can see at the cross section, the top half of the member or the cross section is subjected to a linearly varying compressive load, whereas the bottom half of the cross section is subjected to a linearly varying tensile load. Here, only one part of the cross section is in compression, whereas in a column, if you cut across the column, you can see that the cross section of a column is subjected to uniform compression, as you can see from the figure. So generally, when a transversely loaded member is bent about its major axis, it may buckle sideways, also known as lateral buckling, if its compression flange is not laterally supported. And the critical loading. What is critical loading? When the applied load is equal to P critical, there is a tendency for the compression flange to bend sideways while the remainder of the section is stable and restrain it from doing so. Hence, it is essential to ensure that the compression flanges are laterally supported. So, depending on whether the compression flange is laterally supported or not, the beams can be categorized into two types. The first one is the laterally supported beams. A beam is referred to as laterally supported beam or laterally restrained beam when the lateral buckling is prevented by providing adequate restraints to its compression flange along the length of the beam. Laterally unsupported beams is the second category. A beam is referred to as laterally unsupported beam or laterally unrestrained beam when the lateral buckling is not prevented. If the laterally unrestrained length of the compression flange of the beam is relatively long, then a phenomenon known as lateral buckling or lateral torsional buckling, also known as LTB, of the beam may take place. So mathematically, in terms of flexural stiffness, the laterally unsupported beams will have an equation given here. EIX by L is very much greater than EIY by L, which means that the flexural rigidity of the beam in the major axis is very much greater than the flexural rigidity of the beam in the minor axis. So here EI refers to the flexural rigidity and E is the modulus of elasticity, IX is the moment of inertia about x-axis, also known as strong axis, and IY is the moment of inertia about the y-axis, also known as weak axis. So let's look at laterally supported beams. In laterally supported beams, the movement of the beam is only in one direction, which is vertical in nature. So it can be solved by mechanics of solids. From simple bending theory, we have m by I equal to sigma by y equal to E by R. So we know that m equal to I by y into sigma exterior fiber or the stresses that are acting in the exterior fiber. This I by y can be replaced with Z sub E, which is also known as section modulus or elastic section modulus in this case. And assuming that the extreme fiber reaches the yield stress F sub y, which means that it is governed by strength, we have m equal to Fy into Z sub E. We multiply and divide by Z sub P, which is the plastic section modulus. We have m equal to Z sub E divided by Z sub P into Z sub P into Fy. So we have m equal to beta sub B into Z sub P into Fy. So this is very similar to the equation that is given in page 53 of IS 800, as you can see from the right hand side. The only difference is the Fy is replaced with Fy by gamma m naught to account for the partial safety factor. Now let's come to laterally unsupported beams. Laterally unsupported beams, the member is not only subjected to vertical movement, but it is also subjected to lateral and it will also twist. How does it twist or how does it move laterally? Basically, when a small amount of force is applied, then it moves vertically. Then when you keep increasing the load, then there is a tendency for the beam to either spend more energy going down or it can also take the easy route by twisting sideways. Since the flexural rigidity of the beam in the minor axis is much lesser than the major axis, it will tend to slightly bow outside, which is in the U direction. And you know that since the top half is in compression and the bottom half is in tension, only the compression flange will have buckling effect. So it will tend to twist as well, whereas the bottom half will be trying to restrain it. So this cannot be solved by mechanics of solids. Why? Because from the flexure equation, m equal to beta sub B into Z sub P into Fy. Here the beam does not reach Fy and hence the mechanics of solids equations cannot be applied here. So this laterally unsupported beams are governed by what is known as stability. So the elastic lateral torsional buckling moment M critical is given as M critical equal to beta sub B into F critical B into Z sub P, where F critical is the critical buckling stress in bending. So the beam undergoes three deformations, U, V and gamma. So the differential equation is a function of lateral displacement U, vertical displacement V and the twist gamma. The lateral displacement and vertical displacement can be obtained using the Euler column equation EI into d square y by dx square plus Py equal to 0. Here the first part is the M internal resisting moment and M sub E is the external applied moment. The displacement in single plane y can be replaced with either u or v. So the external moment M sub E can be replaced with the component of external moment. In this case, it is m naught. So the lateral displacement, the equation can be EI into d square u by dx square plus my equal to 0. And for vertical displacement, we have EI into d square v by dx square plus mx equal to 0. And then for twist, we have to come up with another differential equations for t. So solving these differential equations gives M critical. Let us understand the stability of a member under twist gamma in the next class. Thank you.